So I would like to present our findings on the digital leakage. In the past, people were thinking that they've got a problem with ingress, but we found out that there is also a problem with egress. And checking the network status for leaking is not only valid question for the aeronautical band, but also for other frequencies. I will explain what we found in regards to influence on communication systems by the digital leaks. Then I'll explain you what new technology for reading leaking signals from digital networks we can use in the real life. Then I'll explain what methods of ranging the leakage sources we are using. This is called time difference of arrival. And I'll show you how this technology can be implemented in an HFC network in a scalable way. So in 2009, Ron Ranach and Ray Thomas were testing what influence of the leaking QAM channels they may expect on transmission in aeronautical band. They were using their spectrum analyzer, a QAM channel source, and a ham transceiver for checking what is going on in 2-meter band. This is a chart from their paper. What we see here, these are results of their test. As you can see in the left-hand side part of the table, there are the signal levels of eventual leakage signal that is in a CW-like carrier form. Here is associated level of eventual QAM channel leaking at same frequency and its expected power. Then we've got indications of the ham transceiver, and these red fields are signalizing the S-meter indications at which they were already having difficulties in receiving transmission in 2-meter band. So they found that QAM channel of this field strength is actually affecting transmission of the ham transceiver. This is a narrow band transmission, and the wide band signal is disturbing that transmission. That interference is causing communication stop. So they were using also camsonics and trilytics leakage detectors at that frequency band of 2 meters. And what were the indications? Indications of camsonics were 10 microvolt, 20 microvolt, and trilytics were similar, while actually the leaking QAM signal was at 200 microvolt per meter and 400 microvolt per meter. It was a controlled environment. So now we know that the QAM channel can really interfere transmission in 2-meter band. What is also clear, this cannot be tested with existing technology, that is, using analog detectors. They are not capable to indicate proper field strength of the QAM channel. So we know that narrowband communication can be disturbed by leaking QAM channels from the cable plant. Well, intuitively, a wider band transmission like LTE, which is like 20 megahertz, would be distorted much stronger than the narrowband. In our discussions with people who are familiar with the subject in the industry, we got the sense that the mindset is that in general, it would be a very rare situation that a leaking QAM signal would disturb LTE transmission because it won't be that strong. The spectrum screenshots and pictures that are on our next slide will show you that this is not the truth. They are actually coming from a complaint made by the LTE provider, and one of the US cable networks was having simply a really bad problem in some area. This is also important here to tell that these leakages were found using a spectrum analyzer and a special antenna. That was possible only because they were doing that from a close distance and they could see the haystack. With a regular spectrum analyzer or a regular analog leakage detector, it would not be possible. And here is an example. This is the location they found the picture. This is the record of their spectrum analyzer. We can clearly see the haystack. For some reason, Verizon people call this Bart's, from Bart Simpson hairstyle. So when we started talking with them about the signals, they say, we see these Barts. What are Barts? So they are using 11 dB Yagi antenna at 780 megahertz here, and they look at that from a distance of 10 feet. So this is really close. The field strength, if we take this QAM signal that it has level of minus 25 dB millivolt and recalculate it to 30 kilohertz resolution bandwidth, then at 10-foot distance, it comes out to 2,200 microvolt per meter. So no wonder that Verizon started looking for the source of the problem. If that was just one location, it wouldn't be a big deal. But here is another Bart. Here is one more. Here is the next one. Some more? Yes. Here we've got more. And the next one, and another, plenty. So what to do with this? There is a complaint about leaking signal. But is the egress the only issue? The egress is the problem of the LTE provider. But the cable operator might have a problem as well. Here is an example of signals that may actually interfere with the cable plant. These are QAM signals, and the black plot is the cellular telephony. As you can see, two QAM channels can be affected at once if there is network shielding deficiency. On this side of the screen, we see QAM channels, and the black plot, these are 8 VSB channels of terrestrial digital transmission. They overlapped two channels at once. It's very difficult to take a snapshot of such a spectrum situation in the real life while the cable operator is encountering problems. So we are showing this just to signalize that the problem does exist, and we do hear from cable operators that they are dealing with situations like that. And here is an example of a device that was found using the new technology. This is the offending device, and it was not detected with an analog leakage detector. It was not leaking at low frequency. It was okay. It was found using new technology. Later, in the lab, we decided to test this device. We put it into a QAM chamber, and here are the results we get. This is terminated chamber itself. There is a reference tap, terminated, violet plot. It's still within shielding requirements. And the leaking tap in the field condition is represented by a yellow line. As you can see, it has proper shielding at the frequency range where the analog detectors work. But it has not good shielding at high frequency. We were trying to fix that thing, and we decided to check what is happening when we exchange the RFI braid to something new, something better. And that tap with new RF gasket is performing within the requirement. There were more taps like that found in that network. It was just a certain series of tap which was causing the problem. And of course, the cable operator was not aware of that. How the new technology works. The new technology can see leaking QAM signals at any frequency. It consists of two pieces of equipment. One is constantly working at the hub site or head end, while there is another one with a field technician in his car or in his hands. At the head end, we take the QAM channel, we down-convert it, digitize it, and take samples according to GPS timing reference. So we know which portion of the signal happens in which time slot. This information is processed and transferred over internet, and the laser is dead. And the wireless receiver in the handheld device, while the handheld device is also receiving GPS coordinates together with GPS clock, and according to that GPS clock, it reads leakage using its antenna, where also a QAM channel is digitized and its samples are taken according to the GPS clock. All this information from internet and from local receiver goes into the correlator circuitry. In the correlator, the timestamps get synchronized. And using radar techniques, we are able to measure the time delay of the QAM channel that originates at the head end and lands at the receiver antenna. So we can measure that time delay. Since we can measure the time delay of the signal that goes through the leakage source and comes to the antenna, and we've got these GPS coordinates. While the car is driving from point 1 to point 2, the equipment takes measurement of one time delay, another time delay. Then it calculates the difference between these 2 points. Next second, it will take another time delay measurement, and so on. Based on a number of the differences between measurements, we are able to calculate very precisely the location of the leakage source. That accuracy would be around 5 even to 3 meters depending on the current accuracy of the GPS. Here is an example of a record and how that location method works. The green dots on this screen, these are the points where there was proper transmission between the handheld and the headend. The samples were received. The pink dots, they are the symbols of the moments when detection of the leakage was made and the record was made according to a certain threshold. The flag is put in a place where the actual leakage source is located. You can see on this graph how the signal level is changing and how the time delay is changing. In the ideal situation, the maximum of the red curve and the minimum of the blue curve would match, would be in the same spot. But since this is a real life situation where our buildings and other things involved, we've got this little shift. It was a real device that was found. You can see that the time delay is changing in very small values, just between 103.08 microseconds and down to 102 microseconds. How the system is organized. There is a handheld unit, which can be used also as a car unit. It exchanges information with the signal processors installed at the hub sites. There can be a number of hub sites. You can drive between the hub sites. It will recognize the place where it works. There can be also a passive monitoring black box field unit that works very similar way to the handheld, which you see on the left side of the upper part of this screen, and collects data for future analysis. All the data is stored in the signal processor at the hub. There is a Linux computer. That data can be accessed by the client software from multiple sources, sites, and the data can be exported to any application. Here are some real-world results. You can see there are many red flags. This is Washington, D.C. All these flags are marking spots where the new technology discovered leakage sources of level greater than 100 microvolt per meter. What is also nice, the new technology allows the user to see almost in real time, in a couple seconds after the leakage source was found, it will tell him the real level recalculated to 10-foot distance. What is the leakage? And this is a good reference for him to either stop and fix it immediately or to wait for the work order that will come. The system allows the users to open and close work orders immediately from the field. Here is a record of the map with the device that we're talking about that was leaking and was not leaking with lower frequencies. It was tested at 729 megahertz frequency. There is on the left-hand side lower corner of the screen the screenshot of the handheld device with the signal visible. The peak represents the time delay of the signal, of the leakage signal. Here is a second example of a QAM leak that was not existing for analog detectors. This is an example for the source that was not found by leakage detectors that the operator is using now. It was a part of a complaint by the LTE operator. They went twice to that location with the analog detector and once with a spectrum analyzer. They could simply find nothing. But with the new technology, it was immediately detected. It was found. The new technology also contains an analog detector for demo purposes. It looks at central frequency of the analog signal. As you can see on these screenshots attached, the analog shows nothing. The digital shows one source. What is also important to say, the new technology would see a couple leakage sources if they were in proximity, and it will distinguish them. Here is the offending device, another tab. And conclusions. This is clear now that egress from digital network resulting of leaking QAM channels is something real, and it can be harmful to communication systems in the aeronautical band as well as for other operators like LTE. And this is also clear that ingress at high frequencies can be harmful to the traffic on HFC network. Status quo leakage detectors, traditional, are not usable for finding this sort of problems. And the new technology is able to detect digital leaks, and that information about the time delay and the methods for location using the time difference of arrival is really extremely accurate. It works as good that you can literally be taken by the navigator included in that system down to the spot where the leakage is present. With the analog detectors, you may find that entire street is leaking and you don't know where it is exactly. But this one shows the point. So multi-path issues are not a problem for our location method because we use time delay, and the time delay can be used as a reference when this is the closest distance. We know that we are really close to that place. Technology is scalable, can be implemented for very small head-ends as well as for large deployments. So I think that was a short and quick presentation. I've been doing my best. I hope you are not starving to death and you are ready to ask me questions. There were some details that I wasn't able to talk about, but I'm open to answer your questions either now or later. So.
Okay. Time for a couple of quick questions.
Yeah, I'll just have a quick one then. Obviously, all your measurements were on overhead plant.
Pardon me? Overhead? Not only. As you could see on the pictures attached to a Verizon complaint, that was also underground. Underground is underground, but they've got these cabinets that are above the ground, so this is clear that it will leak. Well, this is simple. That high frequency would rather stay underground than leak outside, especially if covered with a metal cover. So that is simply very high frequency.
Does the time delay work by measuring that the packet's been resent because it was destroyed by the noise, or how does that process actually work? Because I'm not sure I understand.
It works as all the radar are working. The radar likes to use as a probing signal noise. So we don't care what is the real content in the QAM signal. we do care for other features of that signal. The higher modulation format on the channel, the more accurate and the better radar built. This is essentially a radar, and it works using just certain features of the signal. It doesn't have to be certain content.
So how does noise generate a latent signal?
The leaking signal?
A latent signal.
Oh, the delay. You see, the noise is just a noise when you look at that with a spectrum analyzer. But if you record it very precisely in time domain, you will see that that noise in this part and in this part is looking different. It has phase. You can modulate noise and you can use it as a carrier. So this is what we use. We use certain phase of that phase and amplitude of the QAM signal, which is essentially looking like noise. And this way we are able to process it in the correlator, and this is one of the ways to read signals that are hidden deep in the noise. While for simple spectrum analyzer, this signal may not be visible, we'll be able to just dig it out from that noise using cross-correlation. We correlate it and we accumulate samples of this correlation results. So if the signals are not in phase, if the parts of the signals are not in phase in correlation processing, they will become like nothing. This is delta Dirac function as response. At the place where they match, they will build up this, like the spike that you could see on the screen.
Second question is the control QAM. Is there a control QAM that's got to be put onto the cable plant, or is it measuring any QAM?
It measures any QAM. We've been doing even tricks that we're connecting our device to the network without telling anyone anything. And we're just driving around and testing it, reading leakages. They were just indicated with the negative time delay. We've been using these tricks as well.
The rest of the plane, later on the plane.
So I'm open for discussion.
You don't add a tag signal at all. You identify a feature in the QAM.
We identify the feature in the QAM signal, so we are absolutely sure that this is your QAM leaking. This is not a different QAM. This is exactly that one.
And you use 3G then to transmit that data to the receiving
Yes.
end, so it can pick up the same point.
Yes. There is also an installer unit that works over ISM band. From the track, it takes samples of the signals that are transferred over G3 to the track, but the technician has a small unit that uses ISM band to take this signal samples. There was a gentleman in that blue shirt who wanted to ask a question, and okay, because I thought that I gave voice to someone else before.
Okay, well, I think, thank you very much, Roman.
Thank you very much.
Okay.